So the goal of today's lecture is to go over motors and ESCs. So motors are obviously very important for us. They're important for a lot of applications. And there are two kinds of motors, brushed and brushless. And they both use magnets and currents. And the short version is when you take a current and flow it through a wire, it generates a magnetic field. And if there's another wire near it that's got current flowing, it will respond to that magnetic field, and there'll be an attractive or a repulsive force between those two wires. So any two wires that have current flowing between them have an attractive or repulsive force, depending on whether the currents are parallel or antiparallel. And that's the physical basis of a motor. So you can imagine if you want to create motion, you can turn the current on so it pushes the wire and then turn it off. And then you can turn it on so it pulls the wire. If you want to change direction, you change the direction of the current. So that's the basis of a motor. It's difficult for me to explain that with PowerPoint. So we're going to watch two YouTube videos that are about one's about 10 minutes, one's about 5 minutes, that have much better explanation than I could ever possibly hope to do. One's about brushed and one's about brushless. Well, let's start with the brushless. This is called a brushed motor because the brushes run along this stator. And that is a friction point and also a high wear point. You can imagine it's spinning around in contact all the time. Sometimes they actually use copper brushes like a toothbrush, but they make it out of copper wire. And that's why it's called a brushed motor. So there's a big disadvantage, which is wear and tear. The lifetime is going to be limited by however long that brush mechanism works. And the friction. But it's very simple. So for that reason, it's a very commonly used motor for low cost applications. It's also simple for the circuit because you notice there is no circuit. There's a battery and there's the motor. Now, by controlling the voltage, you can get more speed or less speed. And we're not going to go into the equations on that, but there's no special circuit to run it. It's called a DC motor, like you said at the end, because you're providing a DC current and a DC voltage. Whatever current voltage you provide, that determines the RPM of the motor. And then the size is determined by the torque. I mean, the size determines the torque, which determines what kind of a load you can spin mechanically. So it's very simple to use, very simple to understand, but has some disadvantages, the lifetime and the friction. So they're commonly used in teeny tiny drones, like these little hand drones. And here's a typical brushed motor. It shows the dimensions. And all you have to do is plug in positive and ground and off you're running. So this particular motor weighs 5 grams, needs about 3 to 5 volts, needs about 0.15 amps, and it can spin at 35,000 to 37,000 RPM. It wants a 75 millimeter propeller. And here are the dimensions. And it's very inexpensive. So this is $17.99 for 8 of them. So it's only a couple dollars each. So this is a very simple motor to use. It's small and you don't need any complicated circuits. So it would be nice if we didn't have that brush mechanism constantly rubbing. If you're going to make a mechanical device, the last thing you want to do is add more friction and also parts that might fail. So the next video is about what's called a brushless motor. So the goal is to have the stator and rotor not touch each other and not touch the circuit. So the question is, how can we accomplish that? And that's a more complicated type of motor called a brushless motor. And that one also we're going to go to YouTube for. But we won't watch the whole video because so here's another Sorry, here's another diagram of the architecture that we're using. It doesn't have the VEC, so there's the microcontroller, there's a PWM signal coming in from your flight controller. There's the plus VCC, which in this case is actually the battery voltage. For you, it would be 7.4 volts. And then there's 6 field effect transistors that can provide high current to the motor. And then there's these ADCs to sense the rotor position, and the FET drivers drive it. So these little blue lines going from the microcontroller to the FET, that's a digital signal, 0 volts or 5 volts, but no current flows through the gate of the FET. The FET is an open circuit. So we don't need to worry about any load on the microcontroller. The gate is actually an open circuit input. There's a little bit of capacitance and that's it. So it doesn't cause any problem to connect the microcontroller digital circuit to the gate of this analog transistor. And when the voltage is 0, the analog transistor is off. When the voltage is 5 volts, the analog transistor is on, but all the current flows through the source and drain of the transistor. Okay, so that's the ESC. And what do we want to do next? Well, so obviously you need a microcontroller and you need some code and you need some sort of a interpreter of the microcontroller to interpret the PWM signal, and then it needs to take that PWM signal and convert it to a series of current pulses, well, voltage pulses on the FETs that then drive the current through the motor. So at this point, we're going to take a vote. There's more theory, but do you want more theory or do you want to go to the demonstration right away? I have a demonstration where we're going to drive the motor with a camera. So I have this document camera here, and I'm just going to show you. Here we go. So there's a motor in there, and I'm going to make it run. I can either do it now and then do the theory later. I can do the theory now and do the motor later. If nobody wants to vote, I'm going to do the demonstration now, because I think it'll make the theory much more concrete for you. So let's go ahead and do that. And I think I would still like to record this. So let's see if it'll record. For posterity. Okay. Okay. So here we go. Probably, yeah, let's do this. If you can't see, let me know. So this is the demonstration of PWM. We'll start with the PWM demonstration. We'll do the motor next. So this is an oscilloscope. Start with this. Here. So here's 4 AA batteries just for convenience. So that provides 4 times 1.5, 6 volts. So this is just a convenient 6-volt power supply. And what I have here is called a servo tester. And is this in your kit? Is this in the kit? No? Too bad. You can borrow it. We have one in the lab. So it's called a servo tester. It says servo. So essentially, what this does is it gives you a PWM output here, depending on how we return this. So it's just like that Arduino video. It's just a simple little tester to provide a PWM output, which can be useful in a lot of different things. So I am going to show you on the oscilloscope the PWM output. So let's see if I can get the oscilloscope going. This is a cheap $40 oscilloscope. So you don't need a really fancy, expensive oscilloscope. So the oscilloscope just displays the voltage versus time of these clip leads. And it goes in the top here. So all I'm doing is displaying the voltage versus time of these clip leads. So what I'm going to do is connect these clip leads to the output of the servo tester. So to do that, I'm going to use a DuPont connector because that's the output of the servo tester. It's the 0.1 inch DuPont connectors. So black is ground. And I have the signal out. So there's our pulses. So as I turn this, the pulses are changing. But it looks like you have the polarity wrong. Is it? Yeah, of course. First thing professor does in a real demo is he gets the sign wrong. All right, there we go. So there's a nice pulse. And you can see as I turn this knob, that pulse width changes. It changes from 1 to 2 milliseconds. Let's zoom in on it. So I'm changing all I'm doing is changing the knob, and that pulse width is changing from 1 to 2 milliseconds. So you can see the maximum is 6, the duty cycle, let's see, the frequency is 42 hertz. It should be 50 hertz. I think that's a slight error in the measurement. And each division here, now I need to change the brightness somehow. Okay, I can't get quite to focus, but each square is 2 milliseconds. So that's a 2 millisecond wide pulse. And we can see, I know why it's, I don't want. Lots of pulses. And so as I turn the knob, those pulses get narrower and wider, but the spacing between the pulses is the same. So the pulses are coming in at 50 hertz, and the pulse width is either 1 or 2 milliseconds, depending on the knob. But let me see if I can do better. We have a little bit of time. Oh, So if I make the time division large, we can see lots and lots of pulses. If I make the time division small, we can just zoom in on one individual pulse. So that's what we want to do. Just want to zoom in on one individual pulse, and let's do the let's bring the offset. Well, you can see that pulse width, right? You see it? That it changes? Even though it's behind the numbers, can you see the pulse width changing? No or yes? Okay. All right. So now I'm going to take a servo and plug it in. The servo is a device that moves its position depending on the pulse width modulation it gets in. So you can see as I turn the knob, the servo turns. So that's a really convenient servo. That's why it's called a servo tester, because you're just giving different pulse width modulation out. So that's the servo responds to PWM signal. Now let's get the motor. So what I'm going to do is pipe this PWM signal into my motor as a demo. So in order to do that, I need a motor. So here's a battery. Here's a LiPo battery, the one that you're going to use for your drone. And let's look at the motor circuit. So there's the LiPo battery. This is the motor you're going to use. It's got 3 wires. So you have to solder. Let's do it like that. There's the motor. And the motor comes with 3 wires. You need to solder them to the ESC. This is the ESC, which we're going to talk a lot more about. So that's the speed controller. It has 3 wires going out to the motor. And then the ESC has this signal connector coming out, which they've already gotten rid of the 5 volts. So it's just a DuPont. So it takes the PWM in from the flight controller. And then this is the battery lead. So let's connect it all up. So I don't want to do the battery yet. Let's connect the output of the servo tester to the ESC. So I'm going to leave the servo there just for demonstration purposes. Guess it can go like that. So as I turn the knob, the pulse width changes on the oscilloscope and the servo is moving. Now this servo tester has a couple more functions. Manual. It's neutral if I press that button. So when I turn it, nothing happens. And then it's got sweep. So it just automatically sweeps it back and forth. So this pulse width goes back and forth between 1 and 2 milliseconds. It does it automatically. So it's a really nice servo tester. However, I don't want to give full throttle to the motor. I don't want to burn it out. If you give full throttle to the motor with no propeller, sometimes you might burn the motor out. So I don't want to do that. So I'm going to go back to manual, and I'm going to make darn sure that I'm at 0 throttle setting, which is 1 millisecond. Now I can plug that in to the speed controller, and now I'm going to plug the speed controller into the battery. And you'll notice the motor is not spinning. So if I turn this, eventually the motor will spin. Now the motor's spinning. So that's how I control the motor throttle. You can hear it spinning. You can see it spinning, right? So that's how your drone will fly. The flight controller will send a PWM output to all 4 speed controllers, and then it will determine how much thrust each motor should provide in order to fly the drone. Your job will be to solder the speed controller, which is actually pretty simple. because you have 3 wires to solder. And there's actually a hole that it goes through, so it's going to be very, very easy to solder. The other end, well, you do have another job for the other end, which is you have to get the power leads to the output of your flight controller. So your flight controller has 2 ESCs out. It needs to be split into 4 individual motors. So the red wire that comes out of your flight controller will have to split into 4 red wires to go to the speed controllers. And then once you do that, your drone will be ready to fly. And you can fly it in the drone cage in manual mode if the radio is working, which was the other milestone. So there's one more thing I want to do on the speed controller, which is look at it. On this side, well, let me unplug it just for, okay. So the brand is BL Heli. And on this side, let's look at the 2 sides. So I was going to use the microscope, but I think this will work. So on this side, there's just 2 microcontrollers. Those are just the digital circuit. On the other side, we can't see it, but I'm going to take the sticker off. And if I bring it up close, you can see the 6 power transistors. If I can get it to focus, maybe if I go like this. Let me put it on something tall. Let's try to hold it. So there are 6 power transistors. No, on the other side. And actually, I don't want that light because it's just adding. If I had the microscope out, you could see it. But I think you can see here. Focus. There's 1, 2, 3, 4, 5, 6 power transistors there. So each one of those is it's a discrete transistor. It's not, there's only 1 transistor in the entire package because they're power and they need to be able to source a lot of current. And then there's some capacitors here. So basically that's all it is. On this side is a microcontroller. On this side is 6 power transistors, and then you're off and running. Well, that's the experimental part for your class. So let's go back to the theory part for the rest of the class. But wait, there's more. Okay, so PWM is easy. It's common. Somehow I didn't get there. So PWM is easy. However, it's an analog protocol. It's the pulse width in milliseconds that's being used to transmit the information. And it's a problem because there may be some noise on that analog signal. Anytime you have an analog signal, it's not immune to noise. A digital signal is immune to noise because if it's 4 volts, if it's 4.5 volts or 4.6 volts, it's always bit 1. And if it's 0 volts or 0.2 volts, it's always bit 0. So a digital protocol is always very immune to noise. But here it's an analog quantity. It's the width of the pulse. And if your measurement circuit isn't perfect, then your throttle won't be exact. So it's not immune to noise. So it's simple and historically was used. However, it would be better to have a digital protocol. So of course, people invented them. So there's several protocols. The most common one for ESCs is called D-Shot. And it is a digital way of sending information, not an analog way. And there are many D-Shots that were invented: one shot, multi-shot, D-Shot, 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 Pro-Shot. So there's lots of digital protocols. Yes? Oops. Give me a little D-Shot. So here's all the D-Shot ESC protocols. I think we're using D-Shot 600. And you'll notice that you're getting 50 pulses per second. That means you can't adjust the throttle any faster than that. So if you're drone racer, you can't have any more fine control on it. So D-Shot are all these different protocols that have various levels of number of bits of resolution. They have error correction and the time resolution. So D-Shot 600 is 26 microseconds. It actually becomes a problem for the microcontroller because they want the speed to go really, really fast. So not all microcontrollers can support all D-Shot protocols. So we're using D-Shot 600, the signal width is 26 microseconds. The throttle update rate is theoretically 37 kilohertz, whereas for PWM it's 50 hertz. And it's 11 bits, so you have 2048 throttle settings. And there's no ambiguity between 0 and 1. With the old-fashioned one, you actually had to calibrate each ESC. It was a real hassle. This one, there's no calibration required because it's digital. Okay, so that's the ESC theory. Now let's talk about the motors. So motors are sized according to their diameter and their height. And that's somehow related to the current carrying requirements, the power input requirements, the amount of torque it can provide, and the size of propeller that it can spin. The bigger the motor, the bigger the propeller. Let's put it that way. But the detailed relationship between those is beyond the scope of this course. And it's mostly done empirically. There is, of course, theory behind it, but in the end of the day, it has to be measured empirically. So we're going to use people's empirical measurements when we do our drone designs. So the bigger the motor, the more the torque, the bigger the propeller can spin. So we're using 1404. So the height is 4 millimeters and diameter is 14 millimeters. Yeah, 1.4 centimeters. Yeah. Okay. And then there's different kV ratings like the video said, which depends on the prop you're using. So here's a picture of it. You can see the magnets and the copper. By the way, be very careful when you're using these motors because they're exposed. There's no cover. And if you have a little piece of metal, it'll get sucked into there. And because the magnets are very, very strong, and then it'll mess up the motor. So if you clip off one of those 0.1 inch DuPont pins and you're within an inch of this motor, it's gonna suck it in. You can go in there and get it out manually with the tweezers, but be careful. Don't allow metal things that are loose near it. Little screws might get in there, so be careful. Okay, so that's the motor theory. Now the props and frames. So prop is specified as diameter and turns per inch and number of blades. 2 blades being the most efficient, but the most noisy. The short reason why they're the most efficient is that the more blades, the more the friction. So 2 blades are the most efficient. So the prop size is specified as XXYY. XX is the diameter in units of 0.1 inch. YY is the pitch, which is the distance the propeller travels during 1 revolution in units of 0.1 inch. So it's like a screwdriver. You can have dense or sparse screws. So our prop is a 40-24. That means we say we're using 4-inch props, and 24 is the pitch. So that's the prop that we're using. And as I've told you before, the design for this course is for education and safety. And it's not for any other purpose. So every time I take this course, I get criticized for the design decisions, rightly so. But this is the most efficient. In fact, this is the only design I know of where you can be under 250 grams and still have GPS autonomous mission. So that was the main reason for this design. Under 250 grams and still be able to do GPS autonomous mission. Okay, so 4024 props. Be careful, there's 2 orientations, clockwise and counterclockwise. We'll get to that in a minute. The other spec is for frame size called a wheelbase. So the 5-inch quad means the prop size, not the frame size. So here's a table of some recommended wheelbases. motor sizes, motor KVs for different propellers. And that have been determined experimentally. This is a 6-inch propeller, 7-inch. And so on, just get bigger and bigger, and you need to consult usually the manufacturer or colleagues that have experience with that. So we're a 4-inch prop. And that's what we do. Here's another table. So I can just provide you references for all these tables. Okay, let's get back to the ESC. So this is the theory part. Now, there needs to be some firmware on there to spin, to create the current pulses. And sometimes students take that as a project, is to write the firmware. There are some engineering schools where they spend a whole quarter just writing the firmware for that ESC, and that's their project. And you saw Arduino was doing that. The YouTube video was doing that with Arduino. He was using a knob, but he could have made that into a small microcontroller like this is and write all the firmware. So like I mentioned in this class, we're not writing code, we're just using existing code. So the specifications for ESC before getting to the firmware are the amp rating and the number of bits. The number of bits, it's either 8 bits or 32 bits. Almost everything these days in microcontrollers is 32 bits. There's very, very few 8-bit microcontrollers left, except for very, very low cost applications, very low performance needs. And this is an application where we don't really need 32 bits. So to save you money, or the school money, I picked an 8-bit ESC instead of a 32-bit ESC. Because I'm trying to keep the cost down so that everybody can have hands-on experience. So we're using an 8-bit ESC. It's a very, very, very old microcontroller, as you can imagine. But it's very, very inexpensive. It's very small and very lightweight, and it's great for a learning tool. Now, what are the firmwares? Well, interesting question. So initially, when drones first came out, there was an open source firmware called BL Heli. And that's what there was probably a precursor to that, but that's what most drone pilots used was BL Heli, and it was useful for the 8-bit. And the developers that created BL Heli decided when they went to 32 bits to make it closed source. So 32-bit BL Heli firmware is closed source. And they charged, like, I don't know what it was, but they charged a small license fee for every ESC that was sold in the world. And they used that money to continue funding their salaries and continue to improve the firmware. And even though I generally prefer open source philosophically, in this case, I'm not allowed to give political opinions, but in this case, that's what they did. And it was a very small added cost ESC. If the ESC is a few dollars, maybe they got a few cents. I don't know exactly what they got. And the drone pilots almost exclusively used BL Heli 32, which was closed source. Now, when the war in Ukraine started, the company decided to close down because they could not guarantee that they would obey legal export control laws and they couldn't guarantee that their software wouldn't be used by Russia. So they closed the company down, and the company no longer exists. And here's a letter from the lawyer. So as of today, it's still closed, and any ESC on the market that's newly manufactured will not legally have BL Heli 32 on. If it was manufactured before 2024, it will. And the arrangement was the manufacturer pre-flashed it. So you didn't actually have to pay BL Heli developers or the company to get the firmware. It was already pre-flashed on the ESC when you bought it. So that is no longer the case. So the state of the art is in flux. And for 32-bit, there's a new open source replacement called AM32. And I haven't built enough drones to know, but from my understanding is that that's comparable in capability and quality to BL 32. So that's the new firmware that you can get from GitHub. You can download the binary and flash it, or you can download the source code, compile the binary and flash it onto your ESCs. Our class is using 8-bit, so this doesn't apply to our class. We're using 8-bit. And we're using BL-HELI-S, which is the 8-bit version of BL-HELI, and that is still open source. That was never proprietary. So that's what our ESCs are flashed with. It's called BL-HELI-S. And you can get it on GitHub. You can compile it if you want, or you can download the binaries, or do nothing. This is one where it's optional. You don't have to replace the firmware. You can leave the firmware on there and your drone will fly fine. The only reason you'd want to change the firmware is, one, if you want to tinker with the settings, and two, if you want it to play a sound when it boots up. So when the drone boots up, the ESCs cause the motors to spin and they play a sound. And I have given you the ability to change that startup boot sound if you want. However, you need to replace BL-HELI-S, which cannot play a custom sound, with BlueJay, which can play a custom sound. So if you want to customize your drone and play a sound, you have to flash BlueJay. But if you don't want to customize it, you can just use it as is. And here's a historical development chart of Simon K. That's when I remember, was in 2011 was what they originally started using. Then BL-HELI, BL-HELI-S, BL-HELI 32 was the, so you can see the microcontrollers. BL-HELI 32 is an ARM STM32. That's what most microcontrollers are these days. BL-HELI and BL-HELI-S were for Atmel. That's the original 8-bit Arduino. And AM32 also is a firmware that can handle the STM32 microcontroller. Okay, and here's the state of the art as a recent. Okay, this is the ESC configurator for BL-HELI, or sorry, for BlueJay. If you want, this is for BL-HELI. So you can actually fine tune the parameters of all the different pulse widths and the throttle setting and the throttle curve and how fast the motor spins and so on. So all of those you can tinker with. And you can configure that in the firmware. I'm not going to do it. I've never done it, but if you're a drone racing pilot and you really want to get every last percentage out of your motor, and you want to fine tune your ESC for your motor and your drone, you do have the ability to go in and change a lot of the parameters in the ESC. And this is the Darth Vader one where I made Star Wars My Startup Sound. And this is the ESC configurator for BlueJay. And you can see there's startup, power, timing, beacon settings, all sorts of settings. So if you want to change the startup tune, you have to reinstall the BlueJay firmware, and then you can load whatever sound you want. You can write your own song. Okay. Now, the last part of the class is, does this just apply to drones? And the answer is no. So the exact same thing that we're doing for drones is used for all brushless motors, including Tesla. So Tesla is another interesting use case of brushless motors. And here is a Tesla motor. They have one. Our life is hard. We have to control 4 motors with 4 ESCs, but Tesla is easy. They only have 1 motor and 1 ESC. So there's the motor and there's the ESC. And you can see the motor has 3 wires coming up. And there's the stator and the rotor. In order to get the stator and the rotor out in this teardown video, they had to hit it with a hammer because it's very tightly integrated. So they get it out, and there's the rotor and the stator. And here is the speed controller. And here are the 6 transistors. So that's not 6, that's 12. So 1 transistor is not enough. So they have to have 4 in parallel. So there's 6 banks of 4. The architecture is the same, but instead of switching on 1 transistor, they switch on 6. And these transistors, when they're off, there's no current flowing, there's no power being dissipated. But when the transistor is on, there's a lot of current flowing. And we talked about the batteries for the Tesla. being able to source 750 amps of current. So it's not a small amount of current that's flowing through these discrete transistors. And they're not perfectly efficient. So ideally, when the switch is closed, the resistance is 0. But when the switch is closed, the resistance is not 0. Let's say the resistance is 1 ohms. Imagine you have 100 amps flowing through a 1 ohm resistor. How much power is that? In other words, let's go back to this architecture. Same thing as a Tesla. Instead of 1 FET, they have 4 in parallel. But let's just ignore that. Let's say there's 1 FET, and let's say there's 100 amps flowing through that FET through the motor. And the FET in the off state is open circuit, no power is being dissipated in the FET. But if the FET in the on state, let's say it's a 1 ohm on resistance, and there's 100 amps flowing through, how much power is being dissipated in that FET? I squared R. So can you give me a number? How many watts? 10,000 watts. That's a lot of watts for one transistor. Now, it's not that bad because it's probably not 1 ohm. Maybe it's 0.1 ohm or 0.01 ohm. Still, 1,000 watts, 100 watts. 100 watts is a light bulb. Imagine grabbing a light bulb and your hand burns, right? Now imagine putting all that power into one single discrete transistor. So they get hot and they need to be cooled. So the Tesla speed controllers have a water cooling system to cool those power MOSFETs because they're not perfectly efficient. So there's a water cooling system in. And this is the MOSFET that they use. And I bought one. I'll pass it around. Bought it for $20. I just bought it for a demo for this class. So it's very interesting. It's silicon carbide, so it's not silicon. And the maximum voltage is 650 volts. The on resistance is 26 milliamps. So it's not 1 ohm, it's 0.02 ohms. And the maximum current is 100 amps. Okay, so everything I just told you and everything you learned about drones is the same principle for all brushless motors, including Tesla and other electric vehicles. The only difference is the power levels and current levels. Okay, now for wiring up your drone, I need to give you a couple practical tips. And this is in the lecture notes, which are posted online. And when I built my first drone, it flipped over because I didn't have the sign right. But this is from the ArduPilot webpage. The arrows in front of the drone. Motor 1 and 2 should spin in counterclockwise. Motors 3 and 4 should spin clockwise. Don't get that wrong or your drone won't fly properly. This is one of the drones I built. I would advise you to label them. You're going to get so confused because there's also many different, you're learning a lot, you're doing a lot of building and wiring up things. And it's hard to keep it all tracked in your mind. And there's different ways of labeling things. So I would advise you strongly to label everything that you're doing, especially the numbers. So it's motor number 1, 2, 3, 4. For example, why did they do it that way? Why don't they go 1, 2, 3, 4 in a circle one way or 1, 2, 3, 4 in a circle the other way? I don't know. I just work here. So label it so you don't forget. And then 1 and 2 have to be clockwise and the other ones have to be counterclockwise. Then in ArduPilot, you need to tell it which output of the flight controller is which motor, which I've already pre-programmed in your parameter file, but I'm telling you where those numbers come from. Servo 5 is motor 3. So motor 3 is the one labeled on the drone. Servo 5 is S5 coming out of your flight controller. So there's a mapping. So here's the mapping. S5 motor 3, S6 motor 4. S7 motor 1, S8 motor 2. Now, I did have one student that really objected to this. Many students have objected to this because I'm mapping S5, 6, 7, 8 to motor 1, 2, 3, 4. And a lot of people don't like that. My first advice is just do it and get over it, okay? If you want to change it, then take the class and then go build your own drone and design it to your own configuration. It's kind of like my parents. When I would eat food in the living room on the couch, they'd say, you can't eat food on the couch in the living room. You got to eat in the kitchen. If you want to eat food on the couch, get your own house. And when you get your own house, then you can eat the food on the couch. So it's kind of like that. But a student, solder S1, 2, is he here? Because I'm going to give him an option to have his own drone because he really wants to do it his way. So he wanted to solder S1 and 2, which is fine as long as the configuration file is right. But then you have to solder and desolder it. It's a little solder thing. Here you just plug it in. So there's many different possible configurations. This one works for me. I advise you to use it. And here's the motor number on the picture. Here's the servo number on the board. So that's what you have to do to wire up the motors to the speed controllers. And then you need the power. As I mentioned, ESC plus and minus go to the ESCs. So one of these needs to go to 4 ESCs plus, and one of these needs to go 4 ESCs minus. So that's your job in the next milestone. Okay, and that's it. So at this point, you have enough information theory-wise to complete your drone build. Put the props on, put the battery on, give it throttle with the radio, and fly it in the drone cage.